evening, everyone. We are in the week 2 problem solving session of the NPTEL course, Control and Tuning Methods in Switch Mode Power Converters. And today's discussion will be about week 2, which is Modulation Techniques in Switch Mode Power Converters. I am Teja Golla. I'm a 5th year research scholar working under Dr. Santanu Kapat at Embedded Power Management Lab, IIT Kharagpur. So let me share my screen. Can you see my screen? Rahul?
Yes, now I can see.
Okay. So today we'll be discussing about a few modulation techniques, but before we go into that, we'll also learn about the design aspects of a switch mode power converter. So I will be discussing about all the design modulation techniques of a buck converter and few problems on buck converter. And Kelvin will be discussing about boost converter. So we have discussed with each other, and we found out that it would be easy if I deal with buck and he deals with boost, rather than both of us dealing with buck and boost and partially discussing about it. So I'll fully concentrate on I'll be fully concentrating on buck converter, and he'll be discussing about boost converter. So all the design aspects as well as the problems that he'll be discussing on boost, and I'll be discussing on buck. So today we'll be starting with the design of buck converter. So I'll briefly summarize the design aspects of a buck converter, then we'll move on to the problems. So I'll be discussing first about the design of the passives offering buck converter. So why is it important to design? Because whenever we are using a buck converter for whatever application, say we want to step down 12 volt to 5 volt or say 1 volt. So we need to first design the buck converter, because we need to know what will be the value of the inductor that we need to use, or the output capacitor, or what type of switch that we'll be using. So these are equally important, because say I can use 10 microfarad, I can use 6 microfarad, I can use 3 microfarad. So if the value of the inductor increases, maybe the size increases. But if I'm over designing, then I'm purposefully wasting my money. Also, it will take up more space. So we need to design it properly so that it will perfectly fit the application where we are designing the buck converter. So we need to first select the components like inductor, capacitor. Load is not in our hands. So when we are designing a buck converter for particular application, that will be the output load current or whatever, it will be decided by the application. So all we have in our hands, input voltage is also not in our hands. It is given by the application. So whatever we have in our like hands is designing the inductor, capacitor, maybe input as well as output, also the switches. So the key things that we need to keep in mind while designing is the switches and the inductor as well as capacitor. So like we also, as a part of our research, we'll be working on some converter. So mine will be multi-phase buck, which is belonging to a buck converter family. So my input and output voltage is fixed, and say my switching frequency is also fixed. Then I need to search for the components, which switch I'll be using, which inductor I'll be using, which capacitor I'll be using. So based on the requirements, as well as based on current requirements and other voltage requirements, I'll first design the inductor as well as design the capacitor and what type of switches I'm looking for. Once I do that, I'll have to do part searching, right? So how will I buy the parts? So there are 3 vendors online which are internationally available. So they are the websites where you can buy components. One is Mouser, one is Digikey. Although this is not covered in the course, I am giving you additional information. So if you are planning to buy, you can buy from this. So these are the websites. You can search Mouser, Digikey as well as Element 14. However, Digikey is famous among these 3. So you can start with the Digikey. But some components are not available in Digikey but are available in Mouser and Element 14. But most of them are available in Digikey. So once you select the inductor, you need to choose a value, also its current rating, and then you have to go to one of these websites, and then there will be filters. You will put the filters, and then you can get the inductor. Maybe I'll show you once we discuss about the design. Maybe I'll quickly show how to select the switches, inductor, as well as the capacitor in Digikey. But before we go into those websites, we need to have a requirement, like what is the value of the inductor that I am going to buy. Then we can use that in the filter. So when we are choosing the inductor as well as the capacitor, like the key or the thumb rule that people follow is, say, let us start with the inductor design. So inductor design is based on the inductor current ripple. So usually we target for 30%, say 30 to 40% of the average inductor current ripple at full load condition. So we'll target say 30% ripple of the average inductor current. So when I say average inductor current, it is not in my hands, right? The load can be 1 ampere, the load can be 10 ampere, the load can be 5 ampere, but we are not going to change the inductor whenever the current changes, right? So we design it for the worst case, which is here full load. So whenever we are saying average inductor current, 30% of the average inductor current for inductor design, we mean full load. So we target full load. Say my full load is, maximum load is 10 amperes. So then 30% of the 10 ampere, which is 3 amperes. So I'll consider 3 amperes. So why 30% of the ripple is usually considered? Because if the ripple increases, then conduction losses increases, right? But if the ripple decreases, then my inductor, or say if I'm, okay, let me write so that it will be more clear. So again, here there are two cases. First case is more ripple. If the ripple is more and if the ripple is less. So if the ripple is more, then your inductance value comes down. Inductance value comes down. If my ripple is less, then the inductance that I need will be more. So what happens if the inductance is less? Then it will be better in terms of performance. Because whenever there is load transient, if the inductance is small, then it will reach the new steady state faster. But if the inductor is more, then the performance will be performance is better. But if the inductor is larger inductor, so you can consider it as it has more inertia. So it will take some time to respond to the transient. So the performance will not be as good as our first case. But what will be better? Because the ripple is less, RMS current will be less, so efficiency will be better. So how to choose between performance or efficiency? So there has been a trade-off, and people considering both of these things in their mind, they have chosen 30% ripple, which is not totally performance or not totally efficiency, but better. So it will have a good performance with good efficiency. So it's a thumb rule that people follow in the industry to consider 30% ripple. So there is a trade-off, and based on this trade-off, they choose 30% ripple. So this is about the inductor design. So now for a buck converter, can anyone tell me how to get the inductor ripple expression? Hello, sir. Shinigami says, will these lectures be recorded and available to watch later? Yes, these lectures are available in my YouTube channel. So let me give the links that you need to keep in mind. So I am sending you three links. One is the meeting link, one is the YouTube channel, and one is the drive where you can access my notes. So whatever I am writing now, this will be uploaded in my drive. So you can access my notes. Also, the lectures are recorded and they will be uploaded to my YouTube channel. So is this clear, Shinigami? Okay. So can anyone tell me how to get the ripple expression of a buck converter?
Yeah, M1 into T1 will be equals to the like delta IL, and
Yes.
M1 will be finding by this
Slope. Yeah, very good.
inductor slope. Yes.
So just to be clear for others, let me quickly draw the inductor. Okay. So say this is something like this, and my say switch is on during this time, and then off during this time, and then again charge. So this is my gate pulse that I call QH high side. So now in this scenario, inductor current will be rising, and then inductor current will be falling, and then again inductor current will be rising. So now the center is called ripple delta again. So we can calculate the slope. During the on time, we know the slope of the inductor current is V in minus V0 by L. So we can write the inductor equation, which is V in minus V0 by L is nothing but the slope, which is delta IL by T on, which is DTS. Or you can also write V equal to L into di by dt. From there also you will get. So now you can get delta IL is V in minus V0 into DTS by L. Right. So I got the delta L expression, but whatever our thumb rule says, it is 30% of the average inductor current. And what is the average inductor current? IL is nothing but I naught, right? Average. So I naught is V naught by R. So say this is equation 1. And we know that equation 2, which is average inductor current IL is nothing but V naught by R. Say this is equation 2. Now we know that delta IL is how much? 30% of IL. So thumb rule, as a thumb rule, whatever we consider delta IL is 30%. So 0 to 0.3 times IL. So now by substituting these equations, we can get the inductance value. So is this part clear for everyone how we design? But sometimes in the question they will say 5% ripple, 10% ripple. That is just to twist the question. But in your application or in practical scenario or like whatever industry follows, this is the criteria they follow. But in the question they can twist the question and change the ripple accordingly, so that you will have to solve it again. Is this part clear?
Yes, clear, Teja.
Okay. So
Teja, here it is given in terms of duty cycle,
yes.
and in the PDF as sir explained, it is given in the form of T on and T on T off.
Yes,
So
yes,
will we
yes,
have
yes.
to kind of be aware of both the cases? Like,
Yes, yes, we'll get to that. Very good point. So you can write in terms of duty ratio and switching time period. But sometimes what happens is input can be varying and the duty ratio is not fixed. However, output voltage is fixed. So when we solve the problems, we'll see how do we design the inductor. And one important thing that we have pointed out is whenever we are designing for the worst case, which means say my input voltage is varying and output voltage is fixed. So duty ratio is varying. So there exists a range of ripple, right? Say if my inductance is fixed, my ripple will be varying depending upon how my input voltage is varying. So whenever we are designing the inductor at the worst case scenario, so at the maximum ripple, whenever at some operating condition, the ripple is maximum. At that condition, the ripple should be 30% of the average inductor current. Maybe at some other condition, it will be lesser, but the maximum should be 30%. So whenever we are designing the inductor or capacitor, we'll design for the worst case, which means at the worst case, when everything is maximum, say the ripple is maximum, in that condition, we target for 30% ripple. So whenever we are designing, we are considering worst case scenario. Also, depending upon the modulation technique. Say if I'm going with pulse width modulation where time period is fixed and duty ratio is varying, we'll write everything in terms of duty ratio because it is dependent on my input output voltage. Sometimes if we go for constant on time where on time is fixed, so we want our expression in terms of on time because on time is fixed, then we can see uh, other variables where things are maximum. So once we solve problems, then it will be more clear, but good that you have pointed it out. So maybe inductor or maybe capacitor, whatever we consider worst case. So at the worst case condition, which will be again maximum input voltage that we'll see, or maybe I'll show you. So delta IL is V in minus V0 into DTS, right? So you know that V0 is nothing but D into Vn. Usually output voltage is regulated, input can be varying. So let us substitute Vn. So my Vn is what? V0 by D, right? Agree?
Yes.
So now if I calculate V in minus V0 into D, so V in minus V0 into D, which is V0 by D minus V0 into D. So if I take common V0 and multiply by D, I'll get V0 into 1 minus D. So now if I write my delta IL again, so delta IL is V0 into 1 minus D into TS by L. So if you consider this scenario, V0 is fixed. Time period is fixed because once we fix time period, then like we are choosing inductor, and say inductance is also fixed. But my duty ratio is varying based on my input voltage. So when will be the ripple be maximum? When so duty ratio again has a range, right? So duty ratio belongs to 0 to 1. It can have 0, maximum value is 1. So when will be the delta EL be maximum?
When D is 0.
D is 0. And say in the application that we have, D becoming 0 is say not possible. Then we can say when D is minimum, delta L is maximum, right?
Yes.
Yes. So delta L is maximum when D is minimum. Say output voltage is regulated, output voltage is fixed, and V in is varying. So when will be the D is minimum? When V in is maximum or V in is minimum? Output is fixed, input is varying from V in minimum to V in maximum. So at what condition D is minimum?
When V in is maximum.
V in is maximum. Very good. So when
Yes.
V input is maximum. So whenever we are designing, we have to design the inductor, I mean the inductor inductance value, considering 30% of ripple when the load current is maximum, also when the input is maximum. So that if at maximum input voltage and maximum load current, if my inductor ripple is 30% of this, then at other conditions it will be lesser than that. So at the worst case scenario, inductance ripple should be 30% of the average inductor. Same with the capacitor, which I'll show you. Is this fine?
Yes, clear.
Okay. Others, what about others?
It is clear, sir.
Okay. So we'll quickly go through the capacitance design also. So I'll copy this and paste it here. Yeah. So now we'll quickly discuss about the capacitor design. So again, this also is for worst case. So whenever the worst case happens, that time we will consider. So here we'll consider 2% output voltage ripple, 2% output voltage ripple, which means the delta VC, the ripple that we are considering should be 0.02 times of output voltage or delta V naught. So delta V naught should be 0.02, say 2% to 5%, but typically people consider 2%. In the question, they can say 1%, 3%. That does not mean that it is taken. Just to test your understanding, they'll give 1%, 3%, 5%. But this is the practical scenario that people consider. So now, how do we design capacitor? So based on the ripple. So first, we need to draw the capacitor current. So this is our inductor current, right? This is our IL. And we know capacitor current is IL minus I naught. So we have to bring it down by its average value. So this is my load current I naught, right? So now capacitor current, if we are drawing capacitor current, I see. So its average value will be 0 and the waveform looks something like this. Average value 0 meaning if we consider the area, so I'm considering this area, the negative area will be equal to the positive area. So this positive will corresponds to the positive ripple of the output voltage, and then both of these corresponds to the negative delta V minus delta V. So like swing, whenever it is swinging around the voltage. So now, how do we calculate the or get the expression? We know that delta Q is equals to C into delta V, and delta Q is what? Delta I into T, right? Or area under the curve. Like this is a product of current into time, which is the area under the curve. So we need to get the area of this curve. So how are we going to get the area of this curve? So you know that the average value of a triangle passes through the midpoint of the height. So the height will be delta L by 2, and the base will be what? It will be dt by 2 because it is coming half below. Sorry, time period by 2 because this is the midpoint. So this is half of the time period. So let me draw. So this is t by 2 and this is delta L by 2. So one is base by 2, one is height by 2. This is from the geometry. So now if I am drawing, it will be half into base delta L by 2 into height Ts by 2 is equals to C into delta V. So now let us bring back the delta L expression from here. And let us substitute it there. So then we'll get that implies half into, so 1 by 8 into V naught into 1 minus D Ts square by L is equals to C into delta V. Now if we are just targeting the delta V expression, we'll get delta V is equals to V naught into 1 minus D Ts square by 8LC. So now say if delta V is 0.02 of V naught, then V naught will get cancelled, and then we'll get the C expression. Or maybe I should put it in a different way. So I'll write C is equals to 8L into delta V. So delta V is a fraction of V naught. So V naught will get cancelled, and then we'll get duty ratio is again we have to target for minimum duty ratio. And then at that minimum duty ratio, switching frequency is fixed, L is fixed. We'll have to calculate the C. And then this is how you design the inductor. Sorry, capacitor. Is this clear?
Yes, clear.
Okay.
Yes.
So now I'll show on the website how to select the capacitor inductor. But I'll just mention a few more things. So whenever we are designing the inductor, so first important thing is the value that you will choose. And then second important thing will be the RMS current that it can support. And third is the saturation current. So as you all know, the BH curve. If it is something like this, when the current increases, the inductor will get saturated, right? So the inductance value at low current and the inductance value at high current is not same. So the inductance value decreases. So L decreases as I naught increases, right? So I think you know this is because of the BH curve. So you have to make sure the inductance that you need at this current, the maximum current, considering the saturation is met, because I will consider say 1 microhenry. but 1 microhenry can become 0.8 microhenry at 10 amperes. So we have to check whether my inductance is 1 microhenry at 10 amperes, and then accordingly you have to select the inductance. And this is very important because else the ripple will becoming more and the efficiency will go down. Similarly for capacitor, if we consider, so capacitor, again first is the value, and then second is the voltage rating, because capacitor has voltage rating. Whatever voltage, output voltage, say 1 volt, you have to choose much higher than that so that the capacitor will not get damaged, else the capacitor will blow. And the other thing is called derating. I'll mention what is derating. So similarly, similar to how inductance value reduces with current, similarly capacitor value, capacitance also decreases as the voltage increases. Say I have chosen 10 microfarad. So the 10 microfarad at 0 volt, so no voltage is connected, will be 10 microfarad. So now I'm connecting it at a load where the voltage is 5 volt. Now it will not be 10 microfarad. It can be 9 microfarad, 8 microfarad, and that is called derating. So we need to choose the capacitance that at the voltage that you are operating will meet this requirement. So I am operating at 5 volt at the output and I need 100 microfarad. So maybe you have to choose 150 microfarad. So with derating, it becomes 100 microfarad at 5 volt. So it is both are quite similar. So this here the inductor gets saturated, inductance value decreases with current. Similarly, here the capacitor value decreases, which is called derating as the voltage increases. So is this clear for everyone?
Yes, sir.
Okay.
Yes, clear.
So now let us go to Digikey. So is my browser visible for everyone? You're
Yes, it's
able to see
visible.
it. Okay. So this is the website where you can get all the components. So let it be capacitor, inductor, switch, op amp, buffer, anything. So I am targeting for inductor. So I will search for inductor and then let us see what will come. So fixed inductor, ferrite beads, ferrite cores. So I need fixed inductor. So you can see there are 150 items. So I'll just quickly go through it. You can always watch the video and then you can do it later, but I'll just show the interface so that you can do it later during your free time. But I recommend you that you go here and then find out so that it will help you in the future. So first thing that you have to do is in stock, because many of them are not in stock. So there is no point in purchasing that. So first you have to put in stock and then say inductor. Say 1 microhenry I need, and there are some standard values which are available more, and there are some non-standard which may be very difficult to get. Say 3.3 microhenry is standard. So if your calculation is saying 3 microhenry, maybe you will not get a 3 microhenry available. So you will go higher. Always higher is better. So 3 microhenry. Say I'm targeting 1 microhenry. So I have selected 1 microhenry and then I'll click apply all. And then now I'll select current rating. Say I am targeting 10 amperes. So I'll target at least 15 amperes. So I'll choose 15 or above, because if I'm getting a higher rated inductor, then it is better. So I am selecting all and then apply all. So these are the basic requirements, although there are additional things which I am not going into detail now. So I have put these filters. One is inductor that I need, current saturation, inductance, and in stock, because I want to buy which are in stock. Also, if you see here, discontinued, last time buy, not for new designs, obsolete, you select active. Because some of the inductors, say they have 10,000 inductors, but they are not manufacturing. Now you have bought the inductor, maybe after 3 months, it will not be available. So you have to click active. And these are the basic requirements that you need to take care of. Now here there is price. So you put increment. So we'll come from the least quality index. Sorry, lowest price. So these are the different companies, Pulse, Kyocera. So if you have requirement on the company, you can select the manufacturer which you want. So Pulse is a very good company. So I want to see what this is offering. So I have opened this link. Now here are the details. It also has data sheet. So here you can get basic details like 1 microhenry plus or minus 20% means it can vary plus or minus. So always we have to go a little bit higher inductance. So at the worst condition, it is fine. So current rating, it is rated for 12 ampere. I was targeting for 10 ampere. So this is fine. Saturation. And then it also has some parasitic resistance, which is called as DC resistance. So now I'm opening the data sheet. So once I open the data sheet, I'll see certain things like it has a part number. So what does correspond to what? Like D is corresponding to grade. This is product series. So you have to see 000 60630. So they are correct corresponding to inductance value dimension, all these things. So now if you scroll down, this is the shape of the inductance from different aspects, top view, bottom view. And yeah, this is what like when they have tested uh, at what temperature. So these are fine. Let me see if we have BH curve. So this is the curve I'm talking about. Say this is our inductor. We have to check whether this is the inductor that we have selected or not. But if you see this curve, whatever I was talking about, say I have ours is 1 microhenry, right? Where is the 1 microhenry? Say this only. Say, for example, consider anything 0.9 microhenry. If I'm operating at 0 ampere or very less ampere, it is 0.9 Henry. But if I'm operating at 15, then the inductance is coming down. Also, the temperature will increase because there are losses in the inductance. So, this is the curve that you need to keep in mind. Uh, Sometimes the inductance value changes a lot drastically. So you have to check at your operating temperature what is the effective inductance. So here it is 0.09 microhenry at 20 amperes. So I have to consider this inductance, not this inductance. So this inductance should meet my requirement. So this is like the things that you need to consider. So in this family, there are different values of inductance. So for each inductance, they have given family. This is, I think, 2.2. This is 3 microhenry, 3.3. So they have given for all. So once you open the data sheet, you will find many details. Considering all these details, you have to choose the inductor. Any questions in inductor? I'm just giving you some information that is not there in the lecture, but it will be helpful in your research or selecting the inductor. If you don't have queries, I'll quickly show capacitance as well. Any queries?
Sir, one doubt.
Yes, yes.
Do we have to separately purchase core, bobbin, etc., or is it
Yes.
possible to get the inductance directly like this?
Okay. Okay. Yeah, very good question. So sometimes, depending upon your application, a direct inductor will be available. In case if it is not available, then you have to buy transformer core, transformer bobbin, and then you have to bind the coil around the core, depending upon how much you want, and then you have to make the custom core depending upon your application. If the value is or the current rating that you are looking for is not available, then you have to make custom made. But most of the scenarios it will be available. In the case of foreign universities, they have tie up with the industry where they will design the inductor and then they will give it to the company. So the company will custom make the inductor. So they have a tool or software where they will select the inductance shape and everything, and then they will give to company and then they'll make. Although in India it is still not being followed.
Okay, sir. One more query.
Yes.
Is it possible to get one inductor? Like, is there any minimum order quantity? Like,
Yes,
we
yes,
have to
yes.
purchase 10 inductors.
Yes, very good. Thank you for pointing it out. So in some cases, like whatever he's saying, it is called MAQ, minimum order quantity. So sometimes the manufacturer says that you need to buy at least 10. So he will not let you buy below 10. So you need to buy minimum 10. So here, if I'm buying one, then I am getting unit price 33. If I'm buying more, then the price will go down. Similarly, for capacitor, it will be drastic difference. One capacitor sometimes cost 40 rupees, but if you are buying 100, you will get for 10 rupees each. So all these are available. So you can press, say I want to buy 50 quantity. Then it will calculate how much 50 quantity will come, and then it will give me price. So 50 per unit I'm getting 27.2. So this is how you can calculate. And then on top of this, they'll have shipping charges, GST. So this is not the final price. You have to log in and then add to cart. And then if you proceed to buy, then the price, some additional price will be added depending upon the taxes. And because there will be, these are not from India. Sometimes they come from Europe, USA. So there will be shipping from there, and there will be custom clearance. So all these charges will be added. But you can give it a try during your leisure time. You can check what are the prices, and yeah, you can do that. Today we'll be solving certain problems. So whatever will be the inductance capacitor that we'll get, you can use that and then design. That will be a very good exercise.
Okay, sir. Okay.
So now let us quickly go to capacitor. So once we go to the capacitor, there are certain capacitors. So some are film capacitors, some are polymer electrolytic will have charge. So most of the scenario we'll use ceramic. So let us go with ceramic. So as I have said, first we have to always keep in stock, and then also here you can put active. Say I need 1 microfarad, which is a very standard. So let us go to 1 microfarad. So 1 microfarad. And then voltage rating, say I am targeting for 25 volts. So I'll keep 25 volt and then apply all. So there is something called package. So if you come here, so these are the package. So what are package? I'll show you package of capacitor. So they are like the size. So yeah. This is a this is one package, this is different package. So if you see some capacitors are small, some capacitors are large. So depending upon the package, if it has to hold, so the how do the size vary? Because if the capacitor has to hold more charge, say if the current is more or the voltage is more, like C Q equal to C into V, if it is rated for high voltage, then maybe the size will be more. So then you have to go for a bigger package. But 1 microfarad standard is 0603. So I'm selecting 0603. So once I do this, usually you have to buy capacitors in bulk because unit price will be very costly. I will show you. Say I'm buying 100 quantity. So you can put 100 here and then put price low to high. Let us do. And again, here there are multiple manufacturers. Sometimes you can go for a standard Alien is there, Taiyo Yuden is there. So this is good. Samsung is also good. So let us go with Samsung. So now if you see, one quantity is 6.87. So if I am buying one quantity, overall price is 6 or say 7 rupees. But if I am buying 10 quantity, then still it is 7 rupees. So instead of buying one, I could buy 10 for almost the same price. So that's why whenever you are buying capacitors, you should buy in bulk. Why usually this happens? Because they need to package the one capacitor and then they send. So it almost takes the same effort for one capacitor as well as 10 capacitors. Also, when you buy in bulk, so they'll make more profit. So that's why the price goes down if you are buying 50. So if I want 100, I can put 100 and then I can click enter. So the meeting is less than a minute. If this meeting ends, kindly join back. So if I'm buying 100, the price is 68 rupees. So accordingly, you can choose capacitors. Yeah, so this is what I wanted to show in addition. But this I always suggest you to do maybe during your leisure time because it will be very important. Whenever you join company, whenever you are purchasing something, it will be always helpful. So just explore. I have shown for Digikey, you can do for Mouser as well as Element 14. The interface slightly changed, but the process remains same. So if you have any questions, you can ask, else we can solve few problems. Clear? Or any queries you have? In case no queries, then we can move and solve for the question. So just I'm reading the question. So consider a buck converter with the following specifications where V input is changing from 6 volt to 16 volt. Output is regulated at 1 volt. Switching frequency is 500 kilohertz. I naught is 10 ampere. Design the inductor for a ripple current of 30% of the average inductor current. Design the capacitor targeting an output voltage ripple of 1%. And what is the duty ratio range? And what is the minimum and maximum on time? And calculate the IL RMS. So because we have already derived it, I will use the result. So I have deliberately given a range of V input so that you will know where to design the inductor. So which voltage we should consider for the design? When I said worst case, so what will be the input voltage that we'll be considering for selecting the inductor? Anyone?
The maximum input voltage.
Maximum input. Yeah. So what is the duty ratio at the maximum input voltage?
1/16.
1/16. Yes. So my duty ratio will be, so for this question, my duty ratio is 1/60. And then time period is how much? In microsecond, can anyone tell? 500 kilohertz. How many microsecond?
That's 2 microseconds.
2 microseconds. Yeah, very good. And then output voltage is already given 1 volt. So what is my design requirement? Delta IL. How much delta IL should I consider?
0.3 of oh, hold on 1 minute.
So this I naught that I have given is like the maximum current. So it can vary from 0 to 10 amperes.
3.
3. Yeah, very good. So I will consider 3 ampere. So can you people calculate and tell me what is the inductance that you are getting? So I'm not solving. So I want you to solve so that uh, you will not make mistakes. All of you, please do. If you have any questions, ask. So I want you to be interactive. So if you have any doubts, you can ask me. But I request you, all of you, to solve the problems along with me. So let me know what is the inductance that I will be looking. So you need to substitute there. V naught is 1. 1 minus D will be 15/16 into TS is 2 micro. So I want inductance in micro. So you can substitute T to be 2 and then delta IL to be 3.
0.625.
0.625 microhenry. Right? Is everyone getting the same answer? Hello.
62.5 microhenry, no?
Yeah, you please check because I'm not calculating. Or do you want me to calculate?
It's coming 6.25 into 10 to the power minus 7. So I think it will be 62.5.
No, it is 6.25 into 10 to the power minus 7 means 0.6 into 10 to the power minus 6.
Oh, okay. Fine. Yeah.
Okay.
That's fine.
So, okay, so inductance is coming 0.625 microhenry. So while selecting, you might go for, because 0.625 may not be available. So you'll go for a higher, say 0.7, 0.8. And also there is D rating. So maybe you will have to go for 0.9 or say 1 microhenry. At 10 amperes, it becomes 0.7. So all these aspects that you need to keep in your mind while selecting the inductor, although design will give you the like fixed number. So when you are practically selecting, we have to consider all these things and then design. So is this clear, the first part of this question? Everyone? If you don't have queries, then we'll move to the second part. So the second part is designing a capacitor targeting an output voltage ripple of 1%. So let us take the result that we have obtained as we have calculated. So I'll be solving all the buck-based design, and tomorrow Kelvin will be solving boost so that we can cover both in detail. So we got to this agreement so that we can have both the exposure. So V naught is 1 volt, and then time period is 2 microsecond, as you have mentioned. So delta V naught is how much? 1% meaning 1%. So delta V naught is how much? 1%.
0.01.
0.01, yeah, very good. And then L you got 0.625, so let us consider 0.625 microhenry. And how much should be the GP ratio that I will be considering? How much GP ratio that I should consider worst case for worst case?
Same, no? 1/16.
Yes, 1/16. So now using these values, calculate capacitance in terms of microfarad or maybe millifarad, and let me know what is the value that you are going. So all of you please calculate. If you have any questions, please ask. So you should clear all your doubts now so that you'll feel comfortable while solving assignments as well as in the final exam.
$69.44 microfarad.
60?
69.44.
Okay, 69.4. Okay, let us see if everyone is getting this. So now we got 69.44 microfarad. Assuming this is correct, say I'm selecting capacitor. So I'll first of all round it off to 70, and then maybe there is derating. So maybe I have to go for 80 microfarad, 90 microfarad, or 100 microfarad. So this derating curves are also there, like in the website. So there you can check. So there are online tools. Maybe I will show you. So is everyone getting the same answer? You please calculate in the meantime. So this is Mauser. So here also we can get. So if you open
Sir, I got
Baroda,
37.5 microfarad.
30.
37.5
Okay. Can others
microfarad.
confirm which of this is correct? So here if you see, this is the like sim surfing toolbox, which is online again. So if I click here, I can get all these graphs. So this is the capacitor derating I am talking about. So if you see at here it is 0%, means the change is not there. But if I'm operating at 12 volts, it has reduced to minus 70%. Say initially it is 10 microfarad or 1 microfarad, it becomes 0.3 microfarad. So from here we can get all these details, how they are changing with the temperature, how they are changing with the DC bias, everything. And then from here you can design. So you always have to go for higher. So one person is saying 37, another student has said 69. Can someone please calculate and tell me so that I can write the final answer before we proceed to the next part of the problem? Hello?
Sir, delta VO is 2% or 1%?
1%. So thumb rule is 2%, but in the question I have twisted it to 1%. So let me call Arun, Naveen, Priya. What is the capacitance that you are getting? Value. Arun, Naveen, are you there?
Sir, for 1% I got 75 microfarad. For 2%
75.
it is 37.5.
Okay.
Yeah,
So
1% is 75 microfarad. Correct.
okay. So then I think I'll go with 75. Priya also saying 75. So I think 75 is the right answer. I have not calculated, so I'm going with the answer that most of you have gotten. So now we have designed. Now, what is the duty ratio range? Third part. Duty ratio range. How do we get? What is the minimum duty
1/6
ratio?
and 1/16.
Yes.
That should be the
So
range, right?
D belongs to 1/16 is the minimum and 1/6 is the maximum. So this is the duty ratio. And fourth one is what is the on time. So what is the on time in terms of duration and time period? What is the on time in terms of duration and time period?
D into TS.
D into TS. And how much is TS in the question?
2 microseconds.
2 microseconds. So what is the on time range now?
1 by
2 by
8
16 to
microsecond to 1 by 3 microsecond.
Okay, yeah. So 1 by 3 microsecond, 1 by 8 first. So 1 by 8 microsecond to 1 by 3 microsecond. So this is the on time range. And what is the fourth question? ILRMS. So how do I calculate ILRMS? Anyone, any idea?
That formula is there, no? 1 by TS into IL square plus
Yes.
IL1,
So
IL2.
yes. So whatever formula that sir has given, that is generalized for any waveform, piecewise linear. But for the inductor current, which is triangular in nature, if you use that formula and solve, you will get this expression, which is IL square plus delta IL square by 12. So this is the expression that you can remember, so that every time you need not calculate. This is standard. So what is IL and what is delta IL that we have gotten?
IL is 10 ampere.
Delta IL? Say at 10 amperes. Delta IL is
Delta
anyways
IL
fixed.
3 ampere.
3 ampere.
3
Delta
ampere.
IL is fixed, IL can vary. Because once inductance is fixed, delta IL is fixed. So now can you calculate IL RMS and tell me how much is the value that you will be getting?
Ten point zero three seven.
10.0. Please. Others, please calculate and let me know if you are getting the same answer. 10.03. Priya also said 10.03.
Yes, this is correct.
So in this
10.06.
question, we have solved inductor for given ripple requirement as well as capacitor for the given ripple requirement. And we have seen that duty ratio can vary. And you have to consider the worst case, which happens to be minimum duty ratio or maximum input voltage for a buck converter. For boost converter, it can be different. So tomorrow, Calvin will be considering one case study where he will be showing. And then we have also seen that on time will vary depending upon the input voltage if the output voltage has to be regulated at 1 volt. And then RMS current also we have calculated. So if you have any questions, you can ask, else we can move to our next concept. Is this fine?
So Teja, just one
Yes.
question, like in general, that
Okay.
is remembering these formulas advisable from the exam perspective, or can we rely on deriving and going? Just your take.
Yes. So whenever like two things you have to remember. One is the uh, like the expression that sir has given. Like for a piecewise linear, you will have that expression, right? 1 by ts into 1 by 3 times x1 x2 plus x1 square plus x2 square. So that you need to remember. So like it will become more handy because every time you need not integrate it. So if you are not getting what I'm saying, let me just show what I mean. So this is the lecture material. So what I'm trying to tell is, you can remember this expression. So you can remember this expression. So which is very easy to remember. So when you have such piecewise linear, so it is 1 by time into individually x1 square plus x2 square plus x1 x2 by 3 into this time period. So this is easy to remember. So that for any given waveform, you can directly apply this rather than deriving it because derivation takes time. But for the switch mode power converters, where the inductor current is triangular, no need to use that formula each and every time. Also, this is a very standard expression for inductor current. So that's why I think sir has also derived for inductor current. And this thing, it is recommended to remember.
Okay, thank you.
And I think this is delta AL square because it is dimensionally incorrect. So that keep in mind. So it will be delta IL square plus delta L square by 12. So this is like a standard one. So it will be good if you remember. So someone else was asking something, I think, in the beginning. Okay, if you don't have any queries, then we'll move on to our next discussion, which is the discontinuous conduction mode. So why is this important, or what is DCM? I'll just briefly summarize. Let us not go into too many details because that is already taught by sir, but I'll just tell what is DCM. So whenever inductor current, say it is high, and the waveform is as shown over here. So now say the average current is reduced so that the value just touches the 0 point. So what I mean to say is, let me quickly draw. Okay, so what I'm doing is I am reducing the output current because output current can vary from low value to high value. So there exists a moment that inductor current will be just touching this value, right? So in this case, what happens? It is just touching just above the 0 value. So these are all IL in different conditions. So this is called CCM because it is continuously conducting. So inductor is continuously there, like inductor current is always there, and it is always non-zero value. Whereas in the second case that we have considered, it is just touching the 0. So this is called critical conduction mode, which is also known as CRM, critical conduction mode. And CCM stands for continuous conduction mode. And what is DCM? Discontinuous conduction mode. Say the average inductor current. So here now, if I draw the average current, it will be the middle of this point. So I0. Say I0 has further reduced. Then it will go negative, right? So say it has gone something like now. What is the issue is, if the ripple of the inductor current remains same and the average value is going down. So average value is going down and then the ripple is also there. So now what happens is, because of this ripple, the RMS current still remains high. Also, this RMS current leads to losses, right? So the losses will be high. Again, the switch will be conducting, right? So there is a current that is flowing through the switch. So whenever the switch is being turned on and off, there will be switching losses. So in order to reduce the losses at light load condition, what mode will be used is DCM. So in this case, what happens is inductor current is always positive, and here there is a diode. So if you see the previous figure, here there is a switch. So whenever there is a switch, both are switches, then it is called synchronous buck converter. When both are switches, and when both are switches, then the current can go negative, and then this type of waveform you can expect. But when you connect diode, then it is called asynchronous buck converter because diode will not allow negative current. it will only allow the forward current, right? So it will be positive. So in that case, the inductor current waveform will look something like this. So it will have positive value, it will become 0, and then again this type of. So now the average value will be something like this, I know. So if the average value is very less, so then there is no need to go for negative current. Instead, we can keep it at 0. So in this case, the losses will reduce. So that's why this mode is used, which is called as DCM mode of operation. Clear? So when the
Yes.
current decreases.
Hello, sir. DCM is the average current.
Sorry.
Hello, sir. DCM is the average current.
No, DCM is not the
Average
average
value.
current. DCM is the mode of operation. So what I'm saying is
Okay.
here, inductor current is above 0, and it is continuously like in a triangle. So this mode is continuous conduction mode. If the value of the inductor current just touches 0, this is CRM. Whereas in the case of DCM, it will become 0 and then stays there. So this is called discontinuous conduction mode. Why discontinuous? Because the triangular waveform of the inductor is discontinuous, because in between it is becoming 0. Although it is continuous, but the mode is called discontinuous because triangles are not continuous.
Okay, sir. Clear.
No. So whenever I naught is low, then DCM is preferable for higher efficiency. So now the question is, can we find the I naught where it is moving from CCM to DCM, or in better words, I can say, can I find the I naught value where CRM exists? So if the I naught is slightly higher, then it will be in CCM. If the I naught is slightly lower, it will be in DCM. So if I am using current, then I will say I naught. If I'm using resistance, so at CCM or at CRM, whatever is the resistance that I have, I'm calling it as RC, which is also called as critical resistance. So can we find this critical resistance so that I know when the resistance changes, either it will go to CCM or DCM. So can we find this critical resistance? Anyone, any idea how to find? Or
Make I naught minus delta IL by 2 equals to 0.
yes, very good. So when this is just touching I naught, we know that it is passing through the midpoint of this triangle, which is delta IL by 2. So I know that I naught is delta IL by 2. So I know I naught and I know delta IL. So let me copy the delta IL expression that we have derived. Okay. So I know delta IL and I know I naught. What is I naught? I naught is V naught by R, right? Because here it is RC, I am considering RC. So now we have to substitute these two in the above equation so that we will get I naught is V naught by RC is equals to delta IL is V naught into 1 minus D into TS by 2L. Right? So V naught get cancelled. So what will be the final expression of RC? Anyone?
2L by 1 minus D into TS.
Yes, 2L by 1 minus D into TS. So this is the critical resistance at which CRM exists. Now I have a question for you. Say I have considered case 1, RC to be greater than RC1 to be greater than RC, and in the second case, RC2 to be less than RC. So in the first case, whether it will be in CCM or DCM, and in the second case, whether it will be in CCM or DCM. So just think about it and let me know.
First case is DCM, second case is CCM.
Yes, very good. So if we are increasing the resistance, it means the current is lesser. So in the case of first case, current is lesser than the CRM case. So current is going down, which means we'll move to DCM. In the second case, we are considering lower resistance, which means it is drawing more current. So it will be shifted up. So it will be CCM. So the first case, it will be current is lesser. So it will be DCM. and in the second case, current is more, so it will be CCM. Is this clear to everyone how we are calculating the critical resistance? Also, if based on the resistance, whether we can say how it is CCM operation or DCM operation.
Yes, sir, clear.
Yes. Okay. So, these are basic summary that I have told. Although sir has told in the DCM how to get the output voltage, everything. Those I am not touching because that will take time. But I am trying to explain why DCM and what is the like necessity for going to DCM and how to get the critical resistance. So now let us quickly solve one problem. So here I have given one buck converter. So let me read the question. Consider a buck converter with the following specifications. Vin is 12 volt, V naught is 1 volt, switching frequency is 700 kilohertz, inductance is 150 nanohenry. Calculate the RC and calculate the inductor ripple current at CRL as well as the average inductor current at CRL. So for calculating RC, as we have gotten the expression of RC, we can directly use this expression and then we can calculate the RC. So first problem or part A, anyone how to, so now that I've given the expression, can anyone calculate and tell me what is the RC, critical resistance? Okay. Arun is saying 0.22 ohm. Let us check what others are getting. Let me write. So others, please let me know whether you are getting the same answer or
0.229.
229. Okay. So 0.23 or 229. So let me consider 229 to be more closer. 229 ohm. So I hope everyone is able to calculate. So this is the RC at which critical conduction mode exists. Now I am asking at critical conduction mode, what will be the inductor ripple current as well as the average current? So how can we calculate ripple current as well as how can we calculate average current? So from this expression, can you tell me what will be the ripple current? Anyone? How to calculate the ripple current? 2 into I naught. So Arun is saying 2 into I naught. And what is I naught?
I naught will be V0 by RC.
Yes, very good. So from this, we can directly calculate. No need to, either you can use this expression or you can also use this expression, but this is very big because you need to multiply 3 terms. Here you can directly get V naught is there, RC is there. So this will make your life simpler. So now can you calculate and tell me what is the ripple?
V naught was 1 volt, right?
Yes, yes. Okay, sorry. Let me show.
Then
V naught is
8.73. Yes.
8.73. Arun is also saying 8.73. So delta N is 8.73 amperes. So I hope everyone is able to get this value. What we have done is we know that at critical conduction mode, delta IL is 2 I know. So 2 V naught by RC and delta IL is 8.73 amperes. So now what is the average inductor current at CRM? Delta IL by 2. Arun is saying delta IL by 2. So we know that average inductor current is nothing but I naught. So at CRM it is delta IL by 2 or V naught by RC. So can anyone calculate and let me know what is the value?
4.36.
So it was 4.365 amperes. So if you see, when we are operating at higher current, delta L is fractional value of the load current, right? When it is at full current, say considering 30%, then delta L is just 0.3 times. But at CRM, if you see, delta L is double of I naught. So like the losses caused by delta L will be more because IRMS is I naught square plus delta L square by 12. Say I naught has become very low, 1 ampere. Delta L will remain the same, right? 8.73. So my RMS current is square root of 1 square plus 8 square by 12. So because of that, the losses will be more. If you go for DCM, then for this case also, like when DCM is in this shape, then you can calculate the RMS current also, considering this to be I naught, I naught 1, I naught 2, I naught 3, and with times. So it will be lesser. The RMS current will go down because there is a region where current is 0. Whereas in this case, we are going negative and RMS current is ripple based. So it will be higher compared to this. So that's why the losses will go down and efficiency will be better if we operate in DCM mode. Now I am asking another question. Assuming the delta IL is considered to be 30% ripple, 30% of maximum I know. What is the full load? So I naught maximum. Can you calculate what will be the I naught maximum? Because ripple current is fixed, right? So in this portion or any portion, ripple current will be fixed once we design the inductor and everything. But I have not given I naught maximum. So assuming that inductor is designed based on the 30% ripple of the I naught maximum, and this is the delta N that we are getting, what is the I naught maximum?
8.73 divided by 0.3. So it is
Okay.
29.1.
29.1. Okay, very good. So it is coming to close to 30 ampere, 29.1. I hope others are also getting the same answer. Clear, everyone? Any doubts before we move to another concept?
No, it's clear.
Okay. So now we'll move to another concept, which is called the modulation technique. So like what is modulation technique? So when we are generating the duty ratio, how are we generating the duty ratio? So this is basically used to generate the gate pulse. So so we need first of all say fixed frequency. So in the case of fixed frequency modulation technique, our frequency has to be fixed. So we'll be using one ramp, and then this ramp is being compared with a control voltage, say fixed control voltage, Vcon, and V ramp, the maximum value is say it is moving from 0 volt to VR. Maximum is say VR, and the minimum is 0, and maximum is VR. So the ramp is changing from 0 to VR, and then the time period is T because I need fixed frequency. And then Vcon is somewhere in between, and this is my on time and this is my off time. And okay, the meeting is less than a minute. So if this meeting ends, kindly join. So in order to generate the gate pulse, VR and this Vcon both are passed through a comparator. So whenever Vcon is positive, so if you see Vcon is having positive, so whenever Vcon is above VR, output will be high. So we are getting the on time, and whenever Vcon is less than VR, we are getting the off time. So can you tell me the relation between T on, T, VR as well as Vcon? So if this meeting ends, kindly join back. So what is the relation between on time, VR, Vcon and T? Anyone? The relation between these four variables, T on T, VR as well as Vcon.
Using similar triangles.
Yes. Yes, someone was telling based on similar triangles. Yeah, your approach is correct. So can you again tell what will be the expression?
Vcon by VR equal to T on by T.
Yes. So VR by Vcon equal to
T by T on.
T by T on. So using similar triangles, so VR by Vcon is equals to T by T on. And T on is what in terms of duty ratio and time?
D into T.
Yes. So T by D into T. So from this, can we calculate what is duty ratio?
Vcon by VR.
Vcon by VR. Very good. So if I want a duty ratio, say 0.6, and then VR is given, this is how we calculate Vcon so that we can get the control voltage value so that I can get a fixed duty ratio. So again, there are two type of modulation techniques I'll tell. So this is the modulation technique that we call it as trailing edge. So trailing edge and then leading edge. So the waveforms are one is the switching frequency, and then another waveform is VR, and then we are getting Q. So switching frequency is something like this, right? And then if you take this one, and then V ramp is something like this. And then this is the control voltage. So this is Vcon. Then we know the gate pulse is something like this. Agree?
The Vcon is connected to the plus side of the
Yes. Okay.
this
Okay.
one,
I
right?
think I'll also write the op-amp. So in this case, the comparator plus and minus. So this is my Vcon, and this is my VR, and this is my Q. Clear?
Yes, this is clear.
So now this is the trailing edge. Now leading edge will be slightly different. So the switching frequency remains same. So the waveform, this waveform will be slightly different. So in the case of leading edge, the waveform will be something like this. But so the edge will vary. And say the control voltage remains the same. And the comparator also remains the same. So the gate pulse will be the opposite. So wherever we have off in the previous case, now we will have on. So now here we'll have on, here we'll have off, here we'll have on, here we'll have off. Is this clear?
Yes, clear.
So now here we are comparing voltages. So they are all voltage based trailing edge modulation, voltage based leading edge modulation. Similarly, we can also do current based when we'll compare the inductor current with reference current. So there, if I have to quickly draw, so similar thing will happen.
Sir,
Yeah.
one doubt.
Yes. Yes.
In leading edge, whether we are giving Q or Q bar to the switch.
Q. Same. So like what happens is if you know controller, so the controller, what it does is it adjusts the gate pulse Q so that my output voltage is regulated. So if this is my modulation technique and this is my duty ratio, so the controller will ensure the Vcon is in such a way that this is the on time. Similarly, here also the controller will adjust the Vcon so that I'll get the proper duty ratio.
Okay.
So the controller will adjust accordingly, but the modulation is different in this case and that case. Similarly, if we are having the inductor current, so then say this is my inductor current, and then we'll have reference signal. So this is our reference signal. So why we call it as trailing edge? Because inductor current is below the I reference. Say this is called I reference, and this is inductor current. Similarly, in this case, it will come at the bottom. Why it is leading edge? Because the inductor is leading. Inductor is above the reference. So that's why it is called leading edge. And we'll study more whenever we go into week 3 and week 4. Sir will be explaining the architectures. Now just I'm giving a brief like introduction about this, but we'll study more about the architectures in the upcoming weeks, and also you'll learn how to make MATLAB models in that. And once controller design everything is shown, I'll discuss about the MATLAB simulations as well. But because the like the triangular waveform is below this, it is called trailing edge. If it is above it, then it is called leading edge. So is this clear how we are generating the gate pulse and everything, waveforms, also the comparator plus minus signals?
Yes, clear.
Okay. So if you have any doubts, you can ask, else we'll solve a couple of more problems. So in this case, I have asked you to calculate Vcon. So a buck converter is given with the following specifications. Input is 12 volt, output is 1.8 volt, switching frequency is 500 kilohertz. Calculate the Vcon if VR is 1 volt for trailing edge PWM and VR is 3 volt for leading edge PWM. So just to have clarity, I will copy this aspect. So first we are solving the trailing edge, right? So we are solving the part A. So this is trailing edge. Okay. So this is trailing edge. So in the case of trailing edge, what is the relation between the duty ratio as well as Vcon and VR, if you remember?
D is equal to Vcon by VR.
Okay. So now can you calculate what is my Vcon for this case? How much should be my Vcon so that I will get
0.15.
0.15.
0.15.
So are others getting the same?
Yes, 0.15.
Okay. So VR is 0.15 volt. So if I give 0.15 volt, then I'll get my target output voltage for this given input voltage. Okay. So now this is trailing edge. Let me try just to push this out. Okay, now we are going for the second part, which is the leading edge. Okay, so this is part B, where we have leading edge. So now this is our on time, right? So this is our DTS. So now what is the relation between duty ratio as well as Vcon and VR?
Same.
Sorry,
Yeah, VR by Vcon equals to T by T off.
or are you making any mistake?
Vcon by VR only, same as before.
Yes, same as before, because if I'm considering this height, which is VR, by this height, which is Vcon, and then this height, which is DTS, and again this height, which is T. So it remains the same. Irrespective of the modulation, we are getting the same because the comparator remained the same. So uh, DTS by TS is equals to Vcon by VR. So we'll get duty ratio still the same, which is Vcon by VR. Is this clear or still you are having any confusion? So I have taken these two triangles. So one triangle I have considered this triangle, another triangle I have considered this triangle. So height by height is equals to base by base. Then you will get this expression. Clear? Any doubts? If no doubts, solve for the second case for the leading edge PWM. If VR is 3 volt and this is the condition, what will be my Vcon?
Three times 0.15 into 3, 0.45.
0.45. Okay, so duty ratio is 0.45. So not duty ratio, Vcon. So one question, will the on times be same in both the cases or will it be different? On time? Will the on time be same in both the cases or will it be different?
Different.
Since D is same and the switching frequency is same, so T on has to be same.
Yes, yes. So if the ramp voltage is changing, Vcon is getting adjusted accordingly, so the duty ratio remains same. So this is what the controller will do. So the controller's duty is to change the control voltage accordingly. So we'll meet the target duty ratio so that the target output voltage will be regulated at the output side. So irrespective of the ramp voltage, the duty ratio should remain same because my output voltage is at fixed voltage and input voltage is at a fixed voltage. So it is my controller duty to change the control voltage accordingly. So now can you tell me what is the on time in this case? If you calculate, what will be the on time?
Time period is 2 microsecond.
Okay.
So in the first case, 2 microsecond into 0.15. So it is 0.3
Yes, very good.
microsecond.
So the time period, if we calculate, on time, if we calculate, it is duty ratio into time period, and duty ratio is 0.15 and time period is 2 micro, so it is 0.3. So my on time is basically 0.3 micro. What is the off time now? T of
1.7 microsecond.
T of is 1.7 micro. Is it clear for everyone? How we are calculating T on T off?
Yes, it's clear.
Okay. So now let us move to our final problem. So in this, I have given a constant on time modulation. So T on is given. And we are asking what is the switching time period if my V naught is 1.2 and V in is varying from 6 volt to 12 volt. So any idea how to solve for time period if on time is given?
First, we can calculate duty ratio from input and output voltage.
Okay. Okay. So let us calculate the duty ratio. So what is the duty ratio? D.
1.2 volt by 6 volt.
Okay. Which is
0.2.
okay. So duty ratio is a fixed value or it also has a range?
It has a range. For the second case, it will be 0.1.
So duty ratio is changing from 0.1 to 0.2, right? Agree?
Yes.
Okay. So now we have actually directly done the second part. So now if how do I calculate the switching time period if my on time is fixed? Usually what happens, my switching time period will be fixed. So on time will be adjusted so that this duty ratio is achieved. But now we are doing constant on time modulation. So this is constant on time modulation. So on time is fixed and the switching time period should vary so that my duty ratio is met. So this is the B part that we have solved first. So now what will be the time period? So how to calculate time period?
T on divided by D.
Yes. So we know that T on is D into TSW. So we are calculating the range. So we'll get TSW1 is nothing but T on, which is 1 micro by 1 is say 0.1. And then we'll get another switching time period, which is 1 micro by 0.2. So what is this value? And what is this value?
10 and 5.
10 micro and 5 micro. So my switching time period is varying from 5 micro to 10 micro so that my output voltage will be regulated at 1.2. So now again, it is my controller's responsibility or duty. Irrespective of whatever is the input voltage, it should adjust the switching time period. So the duty ratio can be in between 0.1 to 0.2, any value, but my output voltage is regulated here. So my switching time period, TSW, belongs to 5 microsecond to 10 microsecond. Okay, now let us go to C. So at what condition is the inductor current ripple at its peak? So let us quickly go back and then get the inductor current ripple expression. So if we say okay, so duty ratio is also not fixed. And TS is also not fixed. So how can we say at what condition delta L is max? Anyone any idea? Because both are varying, right? So if one is varying, then we can say that when this is maximum or minimum, delta L will be maximum or minimum. But two variables are changing, so now the possibilities increase. So how are we going to decide at what condition the delta L is maximum or it is minimum?
We can write Ts in terms of T on and D.
Yes. Yes. Very good. Very good. So
Then T on is constant.
yes, T on is constant because in our previous cases, switching period is constant. So we write in terms of switching time period. But in this case, on time is constant. So we have to write in terms of on time. So we know that Ts is what? T on by D. Also, say I don't want to write in terms of D. I can convert into D is V0 by V. So I can also do that. But let us fix with D. So now from this, I want to calculate what is 1 minus D into Ts. 1 minus D into Ts is what? T on by D, right? So it is 1 by D minus 1 into T on. Agree? Everyone?
Yes.
So now if I write final expression, delta IL is equals to V0 into 1 by D minus 1 into T on by L. So this is the overall final expression that we are getting. So now tell me, delta IL will be maximum when D is maximum or when D is minimum?
D is minimum.
So delta IL is maximum when D is minimum. So when is D minimum? When V is maximum or V is minimum?
V in is minimum.
So V is minimum or maximum?
Maximum.
Minimum.
Right. See.
Sorry.
is,
Maximum. V0 by
V
V.
not by Vn, right?
So V is maximum. So V in is maximum. Okay. So because it is in terms of D, so now what is the duty ratio that we need to consider for the calculation? Delta L calculation. Which duty ratio will be considered, 0.1 or 0.2?
0.1.
0.1. Okay. So can you calculate and tell me what is delta IL maximum? So 0.1, consider 0.1. Okay, Navin also says 0.1. So please note down the values so that I can scroll my screen. Vin is varying from 6 volt to 12 volt. V naught is 1.2 volt. On time is 1 microsecond. Duty ratio is 0.1 to 0.2. So once you have noted this down, then I'll scroll down so you can see the formula and you can calculate. Please let me know when I can scroll down. Have you noted down?
Yes, sir.
So now you can use this to calculate delta L maximum. Or you can also do one thing, you can also calculate delta L minimum so that we can see the entire range of delta L for this.
Sir, can you show the value of L once more?
Okay, L is okay, L is not given. Let me give L. So L is 220 nanometer. So L is not given. Assume L is 220 nanometer. Mean is 6 volt to 12 volt. V naught is 1.2. On time is 1 micro. L is 220 nanohenry. Duty ratio is varying from 0.1 to 0.2. And this is the expression for delta L. So I need delta L maximum, which is when D is minimum, and delta L minimum when D is maximum. So I want both the ripple values.
Uh, 49 and 21.8.
Sorry, 40.
49,
Okay.
21.8.
1.4. So I think our delta L is like not in the correct range because of the L value. So what I will do is I'll change the L value because I have not designed, so that's why I have given the L value. So like let us make L to be 3.3 microhenry, or say 3.3. Okay. Use L 3.3 microhenry and then calculate back because we have not designed L properly and these are not practical values. The delta L cannot be this much big. So I have given 3.3 microhenry. L changed.
1.45 and 3.27.
Maximum is 3.27.
3.27.
Okay. 3.27 amperes. And minimum
1.45.
1.45. So others are also able to get the same value? Or are you getting any other value? L is 3.3 Henry because ripple cannot be abnormally high. So I have changed. Kindly let me know. Maybe I'll ask. Anusri and Naveen and Rahul, are you getting the same value for L 3.3 microhenry? So Anusri is saying yes. Okay. So this completes our today's discussion. Kindly let me know if you have any questions. I'll address them. I'll just briefly summarize and then we can wind this session. Do you have any questions?
Sir, one doubt regarding MATLAB simulations.
Okay.
Sir has simulated buck converter in that
MATLAB.
lecture.
Okay.
But in for research purpose, when we take one converter, there will be many modes of operation, like 4 modes or 5 modes.
Yes.
So is it possible to extend this idea to that level, or we have to use the blocks in Simulink?
No. Actually, you can make. So I'm not sure whether sir has already covered the DCM mode of operation. I guess he has covered. So where he will can generate the gate pulse Q, including the DCM operation. So it is our logic that we need to put so that DCM operation is also covered. So it will cover multiple modes of inductor. So we need to make the Simulink in such a way so that it will consider all types of operation, including DCM, CCM, everything. So diode will be there. So you need to put a logic so where you will cross check whether ripple current is more than I naught by 2 or like sorry 2 I naught or it is less than 2 I naught. And then if it is, then you have to forcefully like not forcefully, like you have to put a logic where inductor current will remain at 0. So this is the logic that you have to do. I think sir has already covered. Okay. If that is clear, then I'll go to Sri Shah's question, how to install MATLAB, any
Yes, sir.
YouTube link,
Okay.
please share. So Sri Shah, you have to create a login in MathWorks. And once you create a login in MathWorks, you have to open and then search for MATLAB 2024A. I think that's what I am using. So you can search MATLAB 2024A download in MathWorks. So I have searched MATLAB 2024A. So I'll go to download and install. So from MathWorks download. So here is the MathWorks website. So I have searched there and then I got the link. So this is my account because I am using my institute mail ID. So using my institute mail ID, it is free. I think you might have also been given access by NPTEL. So here are different variations. So I'll select 2024A because I am using 2024A. Also, you can use 2024 25A also. So now you can download for Windows, Mac OS. You can select these options and then click for download. So once it is downloaded, it will be a zip folder. You have to unzip it and then extract it and then run the .exe file. So that's how you will download. So I hope that is clear. Okay. Okay, so just to quickly summarize, today we have discussed about the design of passives of a buck converter. First, we have discussed how to design inductor as well as capacitor based on the thumb rule. And then we also got the expressions. Then I have shown what are the key aspects that you need to keep in mind while designing the inductor and capacitor and how the same can be used as filters in Digikey. Although I have shown only Digikey, you can later explore Mauser as well as element 14. Due to time constraints, I have not shown, but it will be also in the similar. Then we have solved one problem where we have implemented the knowledge that we have learned, which is designing capacitor inductor, and also we have seen that duty ratio as the range. So the on time will also have a range, and we have also seen how to calculate the RMS current. Then we have also seen why DCM is needed, what is the difference between synchronous and asynchronous converter, buck converter, and what are CCM, CRM, DCM operations, and how to calculate the critical resistance where CRM operation happens. And then if the resistance changes, whether it is moving to DCM and CCM, that also we have discussed. And then we have solved quickly one problem to learn how to calculate the critical resistance for given specifications. Then we have moved on to the modulation technique, where we have seen how to generate the gate pulse using trailing edge modulation as well as the leading edge modulation, which are voltage based because it is comparing with the voltage. If we are comparing with current, it will be current based leading or trailing edge modulation, for which also I have provided one example, but the more details of current mode control, voltage mode control architecture will be discussed in the upcoming weeks. Then we have solved one problem where based on trailing edge as well as leading edge PWM, how to calculate the control voltage if VR is given and for a particular duty ratio. In the final problem, we have solved where constant on-time modulation technique is used and on-time is fixed, and how switching time period is changing when the duty ratio is changing. Also, how the duty ratio range can be calculated and how to calculate the inductor current peak. So we have calculated the maximum and minimum, and we have also learned how for different modulation techniques, how can we get the condition for when delta L is maximum. So we have to convert everything into constant variables, and then we have to see when which variable is maximum or minimum, delta L is maximum or minimum. So this is all about this week. If you have any queries, you can ask, else we can end this session here. Okay, if you don't have any questions, then we can end this session here. And I wish you all the best for your assignments. Take your time, solve all the problems. And if you have any doubts, you can ask in my YouTube channel in the comment section. I'll try to address them. And also these videos will be uploaded to my YouTube channel where you can access them. And also my notes will be uploaded to my drive where you can access them. So I wish you all the best. Again, see you in the next week with week 3 problem solving session. And thank you for joining. It was a nice session. So with this, I'll end this session. Okay. Thank you, Arun. Thank you, Anusri, and thank you, Naveen. So with this, I'll end this session here, and I'll meet you again in the next week, Monday, 6 to 8 p.m. Okay. Then good night, everyone. Thank you for joining. I'm ending this meeting.
Thank you, Teja.
Yeah,
Good
thank
night.
you. Good night.